Success would be green, right? Success is green. A failure, not green. Anything else? Independent.
Yeah.
Is the color of each Skittle independent of the previous one chosen? Yeah, they don't affect, N. Unless they melt. Number? Do we have a set number? 5. And then S, the probability of a success? Is what? 20%, right? Now, let's come back for a second to independence. What does that mean? The color of one Skittle does not affect the next, right? However, if I have 10,000 Skittles, and I know 20% of 10,000 is 2,000, right? So if 2,000, so probability of that first one is 20 or 2,000 out of 10,000, right? But if I don't put that Skittle back, will the probability be the same for the next one? No. So really, this one is not independent because that probability is changing. It's not independent. Although the colors aren't really going to change, the probability of drawing that color does change. You with me? So that is where this one actually fails. And it really fails here. And it actually fails here because once you start dividing, because originally it's divided by 10,000, right? But if you draw one Skittle, then you start dividing by 9,999. And draw another one, you got 9,998. You with me? So those probabilities are changing. It's slight, but they are changing. So if it fails with this, then actually this probability of a success is changing. So is this going to fail? It doesn't work. Now, we're getting there. We're working towards it. You watched it. All right, find the probability of getting 5 green Skittles if it's not binomial. So first one is green. So probability of 5 green. Okay, so we're just going to write it out. Probability of that first one being green out of all 10,000 would be 2,000, right? Times, okay, if I took a green out, how many greens are left? And I'm down to 9,999, right? That would be the second green. What would be the third green? And this would be 9,998. Keep going. I know, I started doing it too. All right, so big fat numbers, right? All right, when I calculate this out, I get 0.000319. Really small probability of getting all 5 greens. Okie dokie. Now let's pretend that we did think it was binomial. Let's see what we would get if we use the binomial formula, even though we know it fails. Binomial formula would say, what did we do? 5 choose, and I got all 5, right? All 5 greens? Times 0.2, because it's 20% green, and that would be to the 5th power. And then probability of failing, not being green, would be to the 0 power, because none of them were any other color, right? And so then would I use binomial PDF or CDF in my calculator? PDF, okay? So this is the probability that x is actually equal to 6. So I would use binomial PDF, where n is 5, p is 0.2, and x is 5. Guess what I get? I get 0.000320. What do you notice? Yeah. If we do it by hand with the actual probabilities, and then we do it by a binomial, they're pretty much the same, aren't they? Okay? Pretty much the same. Now, why do you think that is? How did that happen? The sample's so large?
Small.
Small? What does that have to do with it?
It's just changing slightly every single time, so it's not going to change very much.
Yeah. These values right in here are tiny little values, right? There's not significant changes happening up here. Because our sample is, what, 5 out of how many? 10,000? That sample's really small, isn't it? So in reality, it is changing the probabilities, but it's not such a significant change that we have to really worry about it. You working with me? This is easier to calculate than this, isn't it? So we want to use that to our advantage. We want to find out, okay, so how small can the sample be for it to work like a binomial instead of having to do it all by hand, right? So let's keep going. Now I grab a huge handful of 100 Skittles this time from 10,000. X is the number of green in a handful of 100. X could be considered binomial because of the 10% condition is satisfied. So what the heck is the 10% condition? It says this, if you watched the video, you know this. This 10% condition says this. If your sample is less than or equal to 10% of capital N, meaning the whole population, then you can consider that as independent. You can treat it as an independent model. Even if in reality it's not quite independent, if your sample is less than 10% of the size of the entire population, then it works the same. 5 is definitely less than 10% of 10,000, right? That's why it worked. Now, we're going to assume that 10% condition is satisfied here. What's the probability of getting at most 11 green Skittles? So let's think. Probability of 11. Now, at most translates to what inequality? Less than or equal to, right? At most 11 means less than or equal to. All right, what function can we use to find a less than or equal to? That's the CDF thing, right? So I'm going to use binom CDF, where n is, this time we're doing a sample of 10, right? Or no, 100. P is still 20%. X is 11. Now I want to define X. X is the number of green Skittles. When you use calculator speak, that's what we're saying with binom CDF, norm CDF, all that stuff. If you use calculator speak, which you're going to, because it's a big time saver, to get full credit on your questions, we've talked about this, you have to label these parameters, right? But you also have to give X context in the question. It's always the number of something. So you need to write out for your readers, okay, this is the number of green Skittles in this question. All right, so let's run that. Binom CDF. See what we get. $100.2 0.0126 basically. .0126. Now, they gave us the histogram on this one, right? What shape is that? Approximately. Symmetric or normal. So we'd say approximately normal. Okay, if it's binomial, okay, we know the shape's normal. How did we find mean yesterday? Do you remember? Yeah, n times p. And standard deviation was? Good. Square root of n times p times 1 minus p. Yep. So let's figure that out. It's 100 times 0.2, so that would be 20, right? This comes out to be a nice whole number of 4. So now it's saying, redo number 5. So remember this one, we found the probability that we get at most 11, right? So now they're saying, okay, don't use binomial distribution, use a normal distribution because it's the normal shape. See what happens. You with me? So this is like that norm CDF. So if we drew our picture, we're saying the mean that we just calculated is 20, right? And it's saying at most 11. 11 is less than 20, so it's to the left. At most would mean I shade to the left. So if I find my z-score, I would do 11 minus 20 over 4. What's that? What did I do? That's not right. Yes,
Can we even use 20? Because we used the binomial method to get that mean, but we're assuming it's not binomial.
we are assuming it's binomial, and the reason we can use it is because it's a normal distribution as my mean.
I thought you meant like normal distribution as opposed to a binomial distribution.
Well,
Meaning it isn't binomial.
we're just saying this binomial looks really normal. It happens to be the same shape, so will we get the same answer if we use normal?
Okay.
We're kind of checking it out. See if we can cut some corners here too. All right. What did I do? No, that's right. Okay. So it's 11 minus 20 over 4. That gives me a negative 2.25 z-score. You with me? So if I put it in standardized picture form, here's 0, here's negative 2.25, and shade, shade, shade. Then I use norm CDF. My lower boundary would be what? Negative big number, right? Upper boundary would be negative 2.25. Mean is 0, sigma is 1. I get 0.0122. Now, these are both probabilities. When I say both, I'm talking about this one we did when we calculated it as a binomial. This one we calculated it as a normal distribution. What do you notice? Really similar again, aren't they? Really, really similar. So when it comes down to probabilities, like this is saying 12.6% probability. This is saying, oh no, am I missing a 0?
Yeah.
I am missing a 0, aren't I? I'm so sorry. Y'all are looking at me like I got 2 heads. This one should have another 0 in it. Why? I'm sorry, I made a mistake. 0.0126, there we go. That makes a little more sense. All right, I just wrote it down wrong. So, it's not 12, it's 1.26%, isn't it? That's what, if I make this a percentage, 1.26% chance of getting at most 11 green. This one is 1.22%. Is there a big difference between that, probability-wise? No. So all this to say, I don't necessarily have to use binomial distribution to find that probability. I could use normal because the shape of the histogram is normal. But remember, I promised you're not going to have to make a bunch of histograms, right? So how are you going to know it's normal in shape without making them? So glad you asked. There's a little trick to the trade here. It's called the large counts test. I'm going to show you what it is. It's just this numerical thing you do, and if it passes, that means that if I took the time to make a histogram, it would be normal in shape. And I don't want you to make those histograms. All right? Trust? All right, so here we go. So the first thing we talked about here was the 10% condition. When taking a random sample without replacement, that's kind of an important thing, of size, and we're keeping this really generic, little n, it's my sample size, from a population of size big N, we can use a normal distribution if it passes the 10% condition, which we said was if little n is less than or equal to 10% of big N, the population. This lesson is kind of like a ramp up to what we're going to do after Christmas. So you won't necessarily see a lot of this till then, but this is kind of the background of where that's going to come from, okay? Large counts condition. This is that handy little test to keep us from having to make histograms, all right? We can use a normal distribution model to model a binomial distribution if two things happen. If n times p is greater than or equal to 10, isn't that the mean, n times p? If the mean is greater than 10, and if n times 1 minus p is greater than or equal to 10. This would be the number of successes. This would be the expected number of failures. You with me? All right, and you'll get this memorized. You'll know this back the back of your hand. Trust. By the time you take your test, it's no biggie. All right, large counts condition. If this works, then you can just use norm CDF. Isn't that handy? All right, let's look at this. Suppose 65% of high school students eat breakfast before going to school. Do y'all eat breakfast before you come to school?
Yeah.
Some of you do. Some of you don't know. Okay. A random sample of 500 students were surveyed. X is the number of high school students in a random sample of 500 who eat breakfast before going to school. Why can X be modeled by a binomial even though this sample was selected without replacement? That is the kicker right here. If it's without replacement, that fails the independent thing on the bins. But why can we still use binomial? Because of the large counts test, right? So I would show that numerically. I would prove it numerically because, don't use the highlighter. Because, what was my sample? 500. Is it less than 10% of what? What's the population in this scenario? All high school students. Is 500 less than 10% of all high school students? In the country? In the world? I think so, right? So 10% of all high school students. So because it passes 10% condition, we're good to go. We can treat it as independent. Now it says use binomial to estimate the probability that 300 or fewer in the sample eat breakfast before going to school. So we're going to use binomial, but we're going to 300 or fewer. So x is less than or equal to 300. So what function of my calculator am I using? Because it does say use binomial. Binom CDF. N is 500. P is what? Good, 0.65. They gave us that in the question. And X is 300. Now I do have to define what does X represent here? Number of high school students who eat breakfast. Okay? All right, if I run that in my calculator, .0113. All right, there it is. Now, justify, why can we use a normal distribution? How do we know if it's normal? That would be our large counts condition thing. All right, so we're going to use those little guys. So n times p has to be greater than or equal to 10. N times 1 minus p has to be greater than or equal to 10. So let's run the numbers, and this is our numerical justification. So it's 500 times 0.65, and it'd be 500 times 0.35, right? Gives me 325. That's greater than 10. And that's 175, which is greater than or equal to 10. So when you justify, you're showing the mathematical proof, and this is it, the large counts test. So I would show both, and then I would say, because they pass, all you have to do is like bracket it somehow and say it's approximately normal. That is a satisfactory proof on how do you know it's normal? Because it passed the large counts test. If you just write the words pass large counts, that is like not answering it at all. You have to have the numerical values. What do you notice about the 325 and the 175? Anything? And the sample size?
They both add up to 500.
Yeah. These two have to add up to the sample size, don't they? For it to be truly binomial, right? It's either success or failure. So there's a little catch for you. They have to add up to 500. It might be a time saver, it might not. But it's kind of a logic thing. Now, we know it's normal. We know because of the 10%, it's going to be independent enough. So now it says use the normal distribution to estimate the probability that 300 or fewer. All right. So now we're going to draw it this way. The mean, remember this is our mean right here, 325. 300 or fewer. So let's find our z-score. What do we still need here? So we know 325. Our standard deviation, we need to calculate that. So 500 times 0.65 times 0.35. $10.66?
Yes.
Sound like right? All right, so then I would do 300 minus 325 over 10.665. Gives me a z-score of negative 2.34, which should make sense because I'm on the left of the zero. Zero is the mean, right? It should be a negative number. Then I do my norm CDF. Lower boundary of negative big number, upper boundary of negative 2.34. What would the mean be? 0, since we're using a z-score. Sigma is 1. So when I do that, point 00964. All right, look at our answers. Are they close?
Very close.
If you rounded this to the 100th, wouldn't it round to 0.01? And that would round to 0.01 also? So although the numbers look a little different, don't they essentially mean the same probability? Yes. So all that to say, binomial distributions do connect to normal distributions, and we're going to use that a whole bunch after Christmas. Check your packets.